Dear viewers, you are my greatest inspiration. You have supported me all these years. Your kind words of appreciation motivate me to keep making more videos. Welcome to my quantum physics video tutorial series. Here in this video lesson chapter, I will briefly explore the fundamentals and the essentials of the subtopic ultraviolet catastrophe, in close connection with blackbody radiation, as a part of my wave-particle duality video tutorial series. You will find separate elaborate video lessons exclusively on blackbody radiation and wave-particle duality in my quantum physics video tutorial series on my channel. You are most welcome to watch and enjoy. It's your ready answer paper for exam. Save your time and score high in exam. The radiation system that's easiest to analyze is the inside of an empty box, so to speak, devoid of matter, to be precise. Let's imagine a hollow metal box with a blackened interior, with fortified impenetrable reflective walls, and a very tiny hole on the wall. This box is in thermal equilibrium, and is filled with radiation that bounces around inside the box, being repeatedly emitted and reflected by the metallic walls. The best practical blackbody is this black box, because practically none of the radiation entering such a hole could escape again, and the radiation would be absorbed inside the box. Let's assume that the temperature inside the box is above absolute zero. This means the inside is filled with electromagnetic radiation. It's a perfectly insulated enclosure in thermal equilibrium, internally containing blackbody radiation. It will emit through the hole in its wall, provided the hole is small enough to have a negligible effect upon the equilibrium. On the other hand, radiation from outside the box hits the hole and gets trapped inside the box, and is not likely to be re-emitted from that tiny hole. The only radiation that emerges from the hole is the radiation that has been bouncing around inside the box. This way, all the radiations would be absolutely completely trapped in this black box. This phenomenon is used by the Rayleigh-Jeans law. Experimental data performed on the black box showed slightly different results than what was expected by the Rayleigh-Jeans law. I'm gonna come to this law later in this video. Mystery of light-emitting bodies represented an enormous challenge for contemporary physics. Blackbody radiation contradicted the theories of classical physics. In the late 1890s, calculations of the spectrum of blackbody radiation, based on classical electromagnetic theory and thermodynamics, ended up in major inconsistencies. Blackbody radiation was predicted by Gustav Kirchhoff. However, it was Max Planck who was able to correctly describe the behavior of blackbody radiation. Now, to comprehend the concept of anomaly or catastrophe, let's saunter through quanta, curve fitting, and infinity. In order to resolve such anomaly that the radiation energy would become infinite at infinite frequencies, Planck made the unprecedented assumption that energy comes only in discrete packets h-nu. The Planck's constant h can be evaluated by fitting theoretical radiation spectra to the experimental ones. It was not until the end of the 19th century that Max Planck came up with an idea of quantization of radiation energy, in attempt of solving the disagreement between theory and experiments. For very high frequencies, the kinetic energy is calculated as h-nu. Please note that it cannot be translated into thermal energy at these frequencies, because this would mean infinite temperatures. Even though Rayleigh-Jeans law was widely accepted, the experimental results from the black box model, in reality, did not match all the way with the theoretical data. Well, we are naturally curious, did not match, in what way? Rayleigh-Jeans law states that the energy density of blackbody radiation can be estimated as a function of frequency, which changes with the square of that frequency. Rayleigh-Jeans law, also called Rayleigh-Jeans approximation, yields approximation of blackbody radiation curves at one of the two tails of the spectrum, the longer wavelength side to be specific. Whereas, Wien approximation has to do with the shorter wavelength tail of the blackbody spectrum. Rayleigh-Jeans law holds just fine for analysis at long wavelengths and low frequencies. However, unfortunately, that's not the case in analysis at short wavelengths and high frequencies. Ultraviolet catastrophe can be defined as the non-persisting behavior in classical physics between observations and predictions. Here you see graphical depictions of comparison between the Planck's law and the Rayleigh-Jeans law, as well as experimental results versus theoretical data, as well as classical versus quantum theories of blackbody radiation, shown in teal versus golden colors. The radiation can be in terms of intensity, or spectral radiance, or energy density, plotted as a function of wavelength, and as a function of frequency. The Rayleigh-Jeans law fails to correctly reproduce experimental results. In the limit of shorter wavelengths, the Rayleigh-Jeans law predicts infinite radiation intensity, which is inconsistent with the experimental results. Radiation intensity has finite values in the ultraviolet region of the spectrum. This divergence between the results of classical theory and experiments is the ultraviolet catastrophe. It shows how classical physics fails to explain the mechanism of blackbody radiation. So, why is this paradox called ultraviolet catastrophe? The Rayleigh-Jeans law predicted that as the frequency of radiation increases, so would the emitted energy as well. At low frequencies, this equation matches experimental results, but at high frequencies it diverges sharply. These high frequencies are in the ultraviolet region of the electromagnetic spectrum, hence this was termed as the ultraviolet catastrophe. Ready lecture notes and study materials are available on request. Please use the comment section below for further academic discussions. Viewers' suggestions and ideas of new video lesson topics are gratefully appreciated. Stay tuned for more uploads. Please remember to like, subscribe, share.